So I'm representing Vanguard Automation, and Vanguard Automation work on the photonic connectivity side of hybrid integration. And in this talk, I want to show you hybrid integration for photonic connectivity using photonic wire bonding and fast attached micro lenses. So photonic wire bonds are free-form optical waveguides which can connect two optical components together and perform the mode matching and compensate for any alignment mismatches. And fast attached lenses are lenses that are printed onto the surface or edge of your photonic components. And this is all done by 3D printing. So at Vanguard, we believe in passive alignment of components, using additive manufacturing with 3D printing to perform the photonic connectivity and assure low losses. So moving? Yes. Okay. This slide shows our motivation at Vanguard, and we want to tackle today's packaging and assembly challenges. This diagram on the right-hand side pretty much symbolizes the challenges. So to find my pointer. So you see here the large mode field size of a single mode fiber, 10 microns. And then in the middle here, the smaller mode field size of a silicon photonics waveguide or elliptical mode field of indium phosphide waveguide. So you have lots of different materials, different mode fields, and to get low loss, you want to match your mode fields. You need, in some cases, to have low loss, high precision assembly alignment. You also need fast and reproducible packaging to make it manufacturable and to be reliable under various conditions, such as the Telcordia environmental testing. And because of this range of criteria, we see that over 70% of the cost of your product is really driven by photonic packaging integration. So Vanguard Automation supplies solutions for performing photonic integration via additive 3D printing. So we have two solutions, as mentioned earlier. On the left-hand side, the photonic wire bonds, which are the 3D freeform optical waveguides that can connect two components together, performing mode field matching and compensating for any access in your assemblies. You also have a very dense integration. The other solution is the fast attached micro lenses, which can be printed onto the edge or surface of your optical components and allow for a relaxation of alignment tolerances. So photonic wire bonds can compensate misalignments for up to ± 13 microns, whereas fast attached lenses can relax your alignment tolerances up to ± 15 microns. So I want to show in the next few slides some recent applications from our partners and ecosystems where they did hybrid integration using photonic wire bonds and lenses. This slide tackles the photonic wire bonds. You can see here on the top here a recent paper from Rochester Institute of Technology, which was published at ECTC this year, where they did hybrid integration onto an AIM reference chip. So on this AIM reference chip, they placed two GFB lasers and connected these lasers to the chip via photonic wire bonds. And then again, coupled out from this chip to a fiber, also using photonic wire bonds. And this entire assembly had an insertion loss of less than around 4 dB. So you have 4 different interfaces to connect with 4 dB loss. Benefit being you do not need to do active alignment for your active components with low loss. And also, because you use the same interface on either side from laser to chip or chip to fiber, you can use the same PDK for your connectivity. Our ecosystem partner, Dream Photonics, have also been providing the same service for a number of years, where they do hybrid integration of lasers on chips and chip to fiber. I think recently they announced they have an ADK with Tara Semiconductor, where they're providing the service with Tara Semiconductor chips. Another example is our recent collaboration with Poet Technologies and Vanguard Automation. So in this collaboration, we are printing 3D micro lenses onto the Poet interposer to maximize the coupling efficiency between the interposer and the lasers placed onto the Poet interposers. These technologies couple and complement each other very nicely because here Poet really focuses on having passive wafer level scaling and processes for their products. So here the lasers are placed passively onto the interposers, and the lenses work to maximize the coupling efficiency, meaning reduce power consumption, and also using less materials to create the interposer, so really reducing material costs. And finally, an example of Simo Electric. So last year, Sumitomo showed at OFC the very first demonstration where a commercial optical module benefited or had a 3D printed component inside their indium phosphide devices. And so with this paper, they've printed the 3 lenses inside the component and really tested these to show that they are industry proven and passed the Telcordia 468 standards, which means going through environmental testing, reflow soldering, die bonding, shock testing, and high power operation. And where Sumitomo saw the benefit here is to improve coupling efficiency, where they're able to reduce their losses by 1.5 dB per lens, pretty significant. Also relax their alignment tolerances up to 1.6 microns and really reduce their chip size. They didn't need the spot size converters anymore on chip. They could use the 3D printed lenses for this and make their chips 25% smaller. So we've shown compatibility with a wide range of materials and platforms with different foundries. It's not all of them, it's a simple selection. So each of these examples, there are 3 here, you'll see fiber on the left-hand side and chip on the right for AMF. Similar for ficonTEC, chips on the left here, fiber on the left and chip on the right. And in this example here with Mentec China, you have fibers here and a wave dart array on the right-hand side. And for each of these connects, we have 1.5 dB loss for fiber to chip. Actually, the ficonTEC results are new from today. You can see here the range of losses for transmission for these loopbacks on chip. On average, 1.5 dB loss. So we have a path to implement photonic integration with 3D lithography for customers and partners. And we do this slowly to really implement the technology into industry. So the first step, we recommend that the industry keeps their standard production process steps and simply adds 3D printed elements with active alignment into their photonic products. The idea here is to prove coupling and yields, but also to prove the components for all different testing and requirements that the customer might have. In the second step, we remove the active alignment necessary and do 3D printing with passive alignment with relaxed alignment tolerances up to plus minus 15 microns, so showing the customer that passive assembly is a viable process. And in the third step, we move to photonic wire bonding and really get the full benefit of relaxed phase tolerances of plus minus 13 microns with a very compact coupling, very high yields, and a high packaging density. This is all done with the Vanguard Sy, which comprises of an array of machines for the 3D printing and pre and post processing of your chips, full software for machine control, process development and management of your processes, a full suite of materials to do the 3D printing and encapsulation, and all professional services, training, feasibility, collaboration, process development, and support and maintenance. And finally, I just want to say that next week we meet us at ECOC in Frankfurt at booth C104. And also we have the market progress talk where you'll hear much more detail about next generation photonic integration from Sebastian Skyfeld. And lastly, questions, but also in terms of what we can do for EPIC members, what EPIC members can do for us. We're looking for collaboration and opportunities where we can really show that this technology is industry viable and works for a wide different range of customers to bring this technology from where it stands into a viable industry proven production process. So thank you.